Good morning, everyone. Thanks for being here. Thanks to the professor for the introduction, and also like to thank the members of the award selection committee for this award, which is really a great pleasure and an honor to receive. So my presentation today, I'll essentially go through basically the research path that I followed during my PhD. So starting with the problem that I was trying to solve, the limitation and the state of the art of previous studies, talking a bit about the modeling, numerical modeling approach I chose, and then I'll talk about theoretical and practical advancement of my research. So looking to simulation of failure process in brittle rocks, modeling mechanical anisotropy of clay shales, and looking to how the damage develops around ground excavation. In the last part, I'll talk about the application of this approach to in situ experiment from the Montreal underground laboratory. So just a bit of a background, clay shales are currently being assessed as a potential host rock formation for the deep geological disposal of radioactive waste. And the reason for this is that because they have very good isolation property, so very low hydraulic conductivity, and also potential for self-sealing of fractures. However, one concern is related to the damage induced around the underground excavation, the so-called EDZ excavation damage zone. So the EDZ has implications both in the short term, when it comes to tunnel constructability, design to support the excavation sequencing and so on, but more importantly, the long term, because fracturing might be associated with an increase of permeability, and so a negative impact on the isolation property of the rock mass. So essentially, the main motivation behind this research is trying to gain a better understanding of how the EDZ actually form in this type of material. And if we can do that, then we can increase the confidence in performance and safety assessment for underground repository. So the material that I researched is the opalinous clay, which is a candidate host rock for deep geological repository in Switzerland. It's a very unique material. It's somewhat defined as a transitional material between hard soil or soft rock. It's definitely brittle, so when it fails, actually fracture. And also is strongly bended, so the mechanical characteristics are really depending upon the loading orientation. And lots of research is currently going on in Montreal, underground laboratory in Switzerland. So the EDZ in opalinous clay really depends on the direction of the excavation with respect to bedding. So what's generally observed is that if you excavate perpendicular to the bedding, excavation is typically stable, and the failure that occurs is typically only stress control. Meanwhile, when you excavate parallel to the bedding strike, failure has been observed, and this failure is heavily controlled by the weak bedding. As you can see here in this picture, with distinctive failure mechanism, shearing of bedding and buckling. The second case, however, is the most relevant for the actual design of the repository, where the bedding is expected to be horizontal. Just a bit of background on previous modeling studies before my work. Essentially, we're mostly continuum-based elastoplastic models. Starting with the work in the early 2000s of Professor Martin and Dr. Lanyon, and then other models by Corkum and Martin. So as such, this model couldn't really capture the brittle fracture process of rock. Some work has been done using these continuum models, QDEC and 3DEC and so on, but the focus there was mostly on the effect of pre-existing discontinuities, not on the fracturing process itself. So with my work, the idea was to use a code that can explicitly reproduce the fracturing process, and this is a code based on a hybrid finite discrete element method. So the real goal was to further develop this method and validate it, and specifically looking at the effect of mechanical anisotropy on fraction nucleation and propagation in shales. To achieve this goal, I would say three main objectives were set. First one, we want to further validate the method in terms of if the method is actually able to capture brittle failure just in rock, not necessarily anisotropic. And in particular, the focus was on the acoustic activity of rock. Once that was done, we focused on the actual anisotropy, so implementing some solution to capture both stiffness and strength anisotropy. And finally, calibrate one of this model based on field measurement from an underground laboratory. Just very briefly how this method works is essentially a hybrid continuous continuum approach where the finite element analysis takes care of the elastic deformation of the rock, and then this is coupled with discrete element algorithms to capture fraction fragmentation using a cohesive element method, and also the interaction of discrete bodies, either if you have pre-existing discontinuities or discontinuities that emerge during the fracturing process. Essentially, the rock is discretized in triangles. The triangles themselves cannot break, they're just deformable, and they capture the stiffness of the material. And between each triangle, we have this full-noded cohesive element, which I use to actually capture the brittle fracture. So the characteristic here of the method is the constitutive model that is implemented at the crack element level. So those crack elements can fail in tension or in shear, and there is a post-peak displacement softening behavior which is governed by the MO1 and MO2 fracture energy in tension and shear respectively. The code that we used was an open source code, and that's because in that way we'll have the flexibility required to add features to the method. So as I said, the first part of the research was mainly focused on further validating the code in terms of can we reproduce brittle failure in rock correctly. And we'll look into can we capture the release of cyclic energy during the fracture propagation process. So this is just a simple example to look into. So this is a simulation of a compression test, no confinement, and there is a pre-existing discontinuity there at the center. So we compress that, and we can simulate the wing cracking, so tensile pressure developing from the flaw. But at the same time, we are also recording the particle velocity on the side of the specimen, as you would do in the laboratory. So you can see we can record synthetic seismogram. So as fracture nucleate and propagate, the elastic energy that is stored in the rock is released, and is released in the form of seismic waves. So we were actually able to use that information to go and locate back the source of the event. So that way we validate the approach also from a dynamic point of view. We also developed a method to actually quantify the energy released by the fracturing process by monitoring the kinetic energy of nodes around the crack, the nucleating and propagating crack. And that energy was verified to scale with the actual energy that is recorded far away from the source. We applied this algorithm to a confined compression test on rock. So the model was previously calibrated, this is a granite model, previously calibrated to match the stress strain response of an actual laboratory test. But then we looked into the actual seismic, the acoustic activity model during the simulation, and we divided the stress strain curve in several stages, and for each stage we computed the acoustic emission, which are plotted here with the color proportional to the magnitude. So as you can see here, there is an increase of magnitude as you approach failure, and also you go from a diffuse distribution of source location towards localized fracture pattern. We actually did some more quantitative analysis looking at the frequency magnitude distribution of this event, and we show that they actually follow the Gutenberg-Richter relationship, with generally a decrease in p-value as you approach macroscopic failure, and also looking at the fractional dimension of the source location, same thing, decrease of fractional dimension, so you go from diffuse source location to localization as you approach failure. Then we start looking to how do we model the anisotropy of the shale. So for the first solution we came up with was this one. So essentially the stiffness anisotropy is simply implement the transversal isotropic constitutive model for the finite element. While to capture the strength anisotropy, we try with this approach, we essentially insert pre-existing cracks into the model, and essentially the anisotropy of strength and failure mechanism emerges as a natural property of the model. So you can see by doing this, you get axial splitting when you look parallel to the bedding, and shear through the intact matrix when you look perpendicular to them. And the strength response actually follow quite nicely the expected U-shaped strength variation. The shear mechanism along the bedding plane, however, is not captured as actual shear failure, but it's captured as a coalescence of those pre-existing cracks via wing cracking. So the issue here is that to reproduce this bedding plane delineation very well, you need a very small element because you need to be able to have a very fine spacing between those pre-existing cracks. So there is some issue when you try to upscale this with the tunnel scale where you cannot use small element. So we need to come up with a better solution. So the idea was to then incorporate the anisotropy directly into the fraction model. So essentially we go and we vary the cohesive strength parameters of the rock as a function of the orientation of this crack element with respect to the bedding. In this case, we assume minimum strength property when you're on the bedding plane, maximum strength properties when you're perpendicular to them, and with a linear relationship in between. And we were able to calibrate the model to reproduce again the U-shaped strength response of the model. And in this case, however, when you load at an angle with respect to the bedding plane, so when you have the lower strength, you actually simulate a real shear failure, which is actually was the objective of this type of model. So then we apply this to a tunnel. So in this case, it would be a circular tunnel, isotropic in situ stress field with horizontal bedding. So we simulate that, and we can look at how fractures start to nucleate. So in this case, you start with shearing along the bedding planes, here in the punch area, which is where the bedding planes are least favorably oriented with respect to the maximum tensile stress. Of course, this is consistent with you could have just find this location by looking at the simple elastic model where you can compare the stress distribution around the tunnel with the distribution of strength of a hypothetical rock core oriented along the tunnel. So you can see here where the stress is greater than the strength. This is where you can expect failure. However, what you can do with the continuum model, you cannot then follow how fracture will keep growing. So in this case, you can see we have slippage along the bedding planes, and this slippage induces some mode 1 fracturing, so extensional failure spalling in the direction perpendicular to them. And if you leave this unsupported, you start seeing some buckling of layers, which is again in agreement with observation this type of rocks. Then we look at what's the effect of changing the in situ stress field. So if you have an isotropic in situ stress field, so for example, in this case, sigma 1 is greater than sigma 3, sigma 1 is vertical. So what you can see is that because of the stress redistribution around the tunnel, the lateral growth of bedding plane fracture is suppressed, because you have increase of frictional resistance, and instead failure tends to propagate in the vertical direction instead. So you end up with a vertical elongated fracture zone. On the other hand, if the maximum principal stress is horizontal, the bedding slippage is greatly enhanced because you have low frictional resistance here. But also interestingly, this fracture can prevent the flow of sigma 1 in the back and the upper, so you actually have less fracturing in the vertical direction. So you end up with this characteristic wing-shaped fracture. In the last part of the research, I was fortunate enough to be involved in the Montreal project, and specifically in this full-scale replacement FE experiment, which is a multi-phase experiment. Simulates the construction, waste replacement, backfilling, and generation of an replacement tunnel according for high-level nuclear waste according to the Swiss concept. So this was done on Montreal underground laboratory in northwestern Switzerland. It's essentially a 50-meter long tunnel, 3-meter diameters, different support measure. In the central section, which is the one we model, we shotcrete and some anchors. Some steel set at the end, and here close to the starting niche. This tunnel was excavated parallel to the bending plane strike, which is the case that we were interested in. The rock mass response during the excavation was monitored using different tools, including measurement of the convergency of the excavation perimeter, extensometers, both in direction parallel and perpendicular to the bedding, as well as some inclinometers in the crown. So this is a perfect case for calibration of a numerical model of this type. So here's some of the actual field measurement for what concerns tunnel deformation. Very large displacement were observed, so with convergency up to 2%. So clearly not compatible with the pure elastic rock mass response. And at the same time, a strong tunnel mobilization due to the presence of bedding, as well as the heterogeneous response here, so non-polar symmetric, and because of the presence of fault. So this was the kind of data that was used to calibrate the numerical model. That and also inclinometer data. So essentially, inclinometer data were able to capture the vertical displacement profile along the tunnel in advance of the tunnel excavation. So this lines here represent the profile of vertical displacement at this point here, or either above the tunnel roof, for different position of the tunnel face. So as you can see, for a given position of the tunnel excavation phase, displacement already recorded ahead of it, so three-dimensional effect. And at the face, the maximum displacement would typically between 30 and 40% of the total displacement recorded at a specific section. So this was the kind of data that was used, given the bidimensionality of the model, to estimate the pre-convergency and then decide when to activate the support. So the model calibration, in the first attempt, we actually tried to match the absolute displacement at all those 4 points with the model, and that was really not possible because of the heterogeneous response observed in the field due to the presence of fault. The fault was at this stage not included in the model. So we just look at relative convergences between these points. And we were able to match quite well what was observed in the field, here in green observation and in gray the model. Again, with the exception of this line here at the bottom because of the fault. And in yellow here you have the elastic model, which clearly under-predicted the displacement. So the model was calibrated, and this was the displacement field at equilibrium, where you can see elastic behavior in the direction parallel to the bedding, and rock fracturing with rock mass bulking in the direction perpendicular to the bedding. The interesting thing, though, with this type of approach is you can actually go back and then look at how the EDZ was actually generated. And here again, a similar mechanism to what was shown before. So shearing along critically oriented bedding planes. Those bedding planes, as they shear, they use some tensile fracture. It's falling here perpendicular to them. And then when you install the support, activate the shock rate, you can stabilize the fracturing process. But in the end, you still end up with an inner zone highly damaged, and then some outer zone where you have isolated shear fractures. You can look at the in situ stress at equilibrium, and you can notice that the stress field concentration of stresses are depending upon the in situ stress. So in this case, the sigma 1 is vertical 6.5 MPa, and sigma 3 is horizontal 4.5. But there's also stress concentration induced by the fracturing process itself. And you can see rock mass they confine APZ, so that's consistent with the spalling. And as you increase the confined stress with that, you suppress the spalling, and you will have shear fracture. So, some conclusion from this work, we verified show actually that for tunnels excavated parallel to the bedding strike, failure initiated with shear on the bedding planes, and then that evolves with extension of the fracturing. And spalling and buckling is promoted by the bedding plane lamination. So if you can control the deconfinement and the slippage along the bedding planes, you can try to control the EDZ development. If in situ interested in isotropic, you can expect a fracture pattern that's substantially different than what you expect under isotropic condition. In general, the model that was developed for this work was applied to underground waste disposal, but can be applied to other problems that involve fractioning of layered materials, such as borehole stability and hydraulic fracture. Finally, some recommendations for future work. There's definitely need to validate more the fracture pattern that was simulated for the FE experiment by going in the field and looking at comparing with fracture pattern from rock cores. They definitely need to look at into the effect of geologic heterogeneity and pre-existing fracture, like the fault that was not accounted for in the model. Definitely need to go to 3D modeling. Something is already been done in sense, especially to look at the effect of the excavation, what happens ahead of the excavation phase. Another important aspect that was neglected in my work is the pressure fluid, so core mechanical effects should be incorporated into this kind of model. And also, some work has also been done in this regard, looking at how to integrate this result into long-term safety assessment for the underground combustion. Finally, some acknowledgement. I want to thank as many people that have helped and contributed, provide support for this work, and I wish to thank specifically the help from my PhD supervisor, Professor Grasselli, and my colleagues Malik Mahbadi and Brian Tatone, and the support from NSTERC, NAGRA, and partners of the Montreal project. Thank you.
For the nice talk. So this plenary session comes to end. So thank all of you for attending. Thank you.
The coffee is outside. Please go and help yourself, but please be back here at 10:40.